Good evening and welcome to everyone who's joining us today on this Friday at 6 p.m. Thank you all for taking time to join. So as you know, this is our second lesson in our series of revision for grade 12 students. And so today in lesson 2, we're going to be covering topics that typically would appear in mathematics paper 2. So what are those topics? So let's discuss. So typically, what you would want to do to prepare for mathematics paper 2 is go through Euclidean geometry. You would also need to cover sections regarding proportionality, and similar triangles. And of course, you would have been introduced to some new topics or essentially new aspects of trigonometry this year. So typically, these are the topics that you would be assessed on, including analytic geometry in your mathematics paper 2. So in today's lesson, we're actually going to be focusing a bit on Euclidean geometry, and I will perhaps touch on some results regarding proportionality of triangles. I don't think I'm going to get to similar triangles, but we'll definitely talk about a result regarding proportionality. So that's what we're going to be covering today. So as I had mentioned before, remember that we have a chat box and we have a Q&A box. So please utilize the chat box to answer some of the questions that I'm going to be asking you, to comment on whether you're following or not, and use the Q&A to ask me any serious questions that you'd like me to answer. So I'll try my best to keep track of both of these things as we move along. Okay. Right, so what I want to start off with today is this notion of proportional triangles. So one of the major results that you will end up learning when this is covered in class, well, I'm sure you've actually done it already. So let's start off with the question. Have you already studied proportionality in class? I'm sure you would have covered this last month, but let's get the response from the audience today. Has this been covered in class already? Have you been exposed to proportionality of triangles? Yes or no? Oh, wonderful. Someone says yes this week. So that's good. So what I'm going to do is I'm going to try to refresh your memory on that, perhaps reinforce the work that you've learned, and let's see how this goes. So I am sure that you've already in some form encountered the following question, right? So you are given a triangle ABC, where D and E are points on the sides of AB and AC as indicated by this question. And we're told that the line DE is parallel to the line BC. So this is the information that's now been provided. The question says that we need to prove that a line drawn parallel to one side of a triangle divides the other two sides proportionally. So essentially, it is saying that this line DE has been drawn parallel to one side of the triangle, in particular BC, and what this line DE does is it will divide this triangle's sides proportionally in the following sense, that we would have AD over BD, so let's highlight that side, AD over DB is equal to AE over EC. And so that's the relationship here. Green over blue, so the green side over the blue side here is equal to the green over the blue side. So we're talking about the lengths of those sides. So this is what we now essentially want to prove. And this is one of the main results that's taught you when you start studying proportionality in school. So what's important here is for you to understand the result, to internalize what it tells you, to be able to prove the result to enhance your understanding, and thirdly, to ensure that you're able to apply the result. So in order to aid our understanding, what I'm going to do is I'm going to prove the result for you, right? And that is actually one of the questions in last year's examination. So it's actually very important that you understand and you know how to prove this result. Again, for the sake of understanding what it is that we want to do, what do we want to do? We want to prove that when we have a line drawn parallel to one side, so when DE has been drawn parallel to BC, as per this picture, what DE has done is that it's divided the other two sides of the triangle proportionally, meaning mathematically AD over DB is equal to AE over EC. So in order for us to go about proving this, we now need to actually do a few constructions on this diagram. So I'm going to add a few lines to this, and let's take a look at what we get. So the first thing that we want to do in order to prove this result is the following. We will construct line BE and line CD. So that's what we're going to do. So let's draw these lines. I'm going to use red. So we will join B to E. Okay, so it's not allowing me to join. So let me draw this free-handed. So we will join B to E. Okay, so my line needs to be a bit more perfect to be straight. It must be a straight line connecting B to E. And then we would also join, as I had mentioned, C to D. Right, of course, the line needs to be perfectly straight. So let's pretend that those are perfectly straight lines joining B to E and D to C. So we've got line BE and line CD. I hope everyone's following up to that point. So observe now from the diagram, if you had to look at this, I've got a triangle AEB. Now in this triangle AEB, what I would like to do is the following. I want to draw a line perpendicular to AB that joins E. And actually this line is going to denote the height, right? So this is the height of that triangle, right? So I hope that everyone's on par. I'm taking it slow. I hope that you followed. So let's in particular quickly draw out that triangle that we want to work with. We want to focus on, for the current moment, on triangle AEB. Right, so if I had to draw that triangle, we've got AB, and we've got E. So of course we have got D somewhere on this. So we've got that line connecting it there. And then we have the height. Which is at a 90-degree angle. Okay, so that line, this line that is drawn from E is perpendicular to AB. Right, so far, does everybody follow what I have done? So this is triangle AEB, AEB. I just want to check the chat box. I hope no one's confused. All we've done is I've drawn new line segments inside this triangle, and I have drawn a line perpendicular to the side AB to generate the height of the triangle. So I'm just awaiting responses in the chat box. So I see there is a response that says yes. So that was one response. Maybe if we could get more, it would give me a better idea. So remember, let's try and be as well, let's participate as much as we can, right? So indicate to me whether you've followed, if you haven't. So we haven't essentially started doing anything in the proof. All we're doing is we are constructing a new triangle within the existing one. Okay, and so I think we've got a few more yeses, so that's good news, so thank you for that. Right, so what I want to do now is I want to look at the triangle ADC in the same way that I had looked at this triangle AEB. Remember, we had drawn the blue line connecting D to C. So if I had to do that, so let's draw it in blue. So then that means I've got AC. Here is AC, so I've drawn it there, and that C is being connected to D and D to A. Okay, so the diagrams are of course not perfect, but this is what we have. So let's say that was E, so that's when D connected to E, and then what I want to do is a similar thing. I now want to draw the line that denotes the height. So from D perpendicular to the line AC, and we observe that I get another height. So that's height H1, and this one would be height H2. So I hope that that bit is clear. We just check our chat box. Okay, so that seems fine. We just had some responses, yes, that you were following, and so that's good. And so let me quickly just draw So I just want to adjust this a bit. Okay, so we have got E, and of course the line that I had just drawn for H2, which is meant to be perpendicular, and so that is H2. So these are two triangles that we've now obtained, and in the one triangle we've got a height of H1, and in the other triangle we've got a height of H2. So this is important because it's going to help us talk about the area of each of these triangles. So let's use that and keep that in mind. Okay, so that's what we've got. And now what I want to do is, remember, essentially, we want to prove that AD over DB equals to AE over EC. That's the goal here, right? So let's do that. So the trick here is to consider the areas of the corresponding triangles. So the first thing that we're going to look at is we're going to look at the area of triangle ADB, and then we're going to look at the area of the triangle ABD. So that's what's actually happening in here, right? So let's construct and let's write down those areas. Sorry, wrong pen. So we consider the area of triangle ADE over the area of the green one. So we first did the area of the yellow, and now we're going to do the area of the green, which is ABE. Okay, so can you help me determine what is the area of ADE? So I'm going to open up the chat box to you. I'm going to try and look at your responses. What is the area of triangle ADE? That's what I'm looking for. Okay, we've got some responses again. So, okay, so before you tell me what is the area of triangle ADE, would you like to tell me what is the formula for the area of a triangle? Maybe that will help guide you. Formula for the area of a triangle. Right, and then we've got some responses. Right, so we've got half base times height. Perfect. So we need to know what is half base times height with respect to my yellow triangle, ADE. Wouldn't it be half times AD times H1? That's half base times height. And I see that there was someone that actually had provided that answer. So I'm just trying to scroll very slowly because we have numerous responses. Okay, so yes, so someone has given us one of the answer. Right, so it's half AD times H1, because in particular, we had seen that the height in that triangle was H1. So it's half AD times H1. Then likewise, I want to know what is the area of ABE. ABE is the following triangle. There it is here. What is the area of ABE? Right. And someone's told me it's half AE. Is that the case? So what is the base? The base of this triangle is AB. Do you agree? Great. So I'm seeing quite a few responses. So the height of triangle, sorry, the area of triangle AEB is nothing but half base times height, which is half AB times H1. So let's put that in. And so we then observe that this is nothing but, oh, apologies. Let's go back. The base of this triangle that we were looking at. So rather, what I want to do is, I don't want to look at right. So we've got our area of triangle ADE, and the other triangle that I want to consider is actually triangle BDE, right? So let's draw our attention to BDE, and let me highlight that one instead. Okay, so in here, we observe that the area for triangle, the blue triangle BDE, let me adjust that. Is half base, the base in here, once again, is BD times H1. Okay, so you can read that as BD or DB, it doesn't matter. And so here we see that this is nothing but AD over BD, or I could write it down as DB. So perhaps for your understanding, let's swap the letters around. So you read it as DB. Did everyone follow what I had done there? So up to this point, I hope that everyone's on board that we have AD over DB by taking the ratio of the area of the triangle ADE over the area of triangle BDE. Let's go back to the picture. Now we want to try and utilize the other triangles that we haven't dealt with yet. So let me try and get rid of the highlights that's already there. So now what we're going to do is we are going to focus. Okay, we've got another question in the chat box. Let's see. Does BDE have a height? Yes, it does. Remember, the apex of both of those triangles was point E. So they have the same height. I will explain this a bit better with a diagram. I'm going to do this shortly, and I'm sure that's going to answer your question and convince you. But before I get to that point, let's quickly talk about the second triangle that we want to focus on. Let's focus now. Let's bring our attention to triangle once again. This time round, we will still talk about ADE. So now we want to talk about the area of triangle ADE over the area of triangle. And now we're going to be careful about what it is that we pick. We're going to pick, so we're going to be working with the blue highlighted triangle, which we can read off as DEC. Right, so I'm talking about area of the triangle DEC. And so what is this equal to? Once again, half base times height. So it's half the base of the triangle this time round. If I utilize the base as AE, then I observe that the height is H2. So it's half AE times H2. So that's when H2 comes into play. And for the triangle DEC, it's half times the base, which is EC, times the height H2. So perhaps my diagram is not lending towards you seeing that H2 is once again the height, but I'm going to explain that very shortly. So it's a half times the base, which is EC, or we can call it CE, times H2. And here we observe that we get AE equals to EC. So up to this point of that proof, have we followed? We have a raised hand. So perhaps you could type your question in the chat box. Okay, so we're at this point. This is what we've done in the proof so far. So observe that I now have this ratio AD over DB and AE over EC. It's certainly starting to look like what I want, but I need to show that these two things are equal. So observe, what do we have on the left-hand sides here? Observe that both the numerators of these fractions are identical. So the only thing that we'd have to verify is if both the denominators are identical. So that's what we would need to check. Okay, someone says they're a bit confused. So let me explain something very quickly right here. So what I have in this picture is I have two. So I've got two lines and they are parallel to one another. Okay, so the line above is parallel to the one below. I've got two triangles that are drawn within these parallel lines. So can you see that regardless of how these triangles were drawn, because the entire extent of these two triangles live in the two parallel lines, they will always have the same height, right? So does everybody agree that that is the case? That when these two triangles are drawn in this specific way, they live between two parallel lines, their height would be the same. So that's what we've got in there. And there is a result that says that the area of two triangles are equal. If and only if they have equal bases and are between parallel lines. So maybe I could use the word drawn between. So in this situation here, if the base of this triangle is B1, and if the base of this triangle is B2, and if I know that the base B1 equals to B2, then the area of the purple triangle will equal to the area of the blue triangle because they had the same bases and they both live between parallel lines. So despite looking different, these two seemingly different triangles actually occupy the same area on the page, right? So that's the idea here. Okay, so let's now go back to this proof, and it is that result that I had explained. When you have things occurring between two parallel lines, they end up having the same area provided they have the same bases. So we will now utilize that result to see why the area of BDE is equal to the area of DEC, right? So that's the key thing. Where is triangle? Let's just see. Okay, right. So the question is, where is triangle BDE? Triangle BDE is right here. Sorry, I dropped out of the call, but I'm back. Let me quickly share my screen. Okay, so I'll just repeat because I'm not sure at which point you had lost me, but we were trying to compare two triangles. The first triangle that we had wanted to compare is triangle BDE, and the other triangle that we want to compare is triangle EDC. So I've got a pink triangle and I've got an orange triangle. So I want you to observe the following. Triangle DBE and triangle DEC actually have the same base. Do you see that? They have like bases, if you view it there. So DE is the common base. Does everybody follow that? I'm just looking for a few responses to see if we're all on par. So we've got these two triangles. I've got the pink triangle and I've got the orange triangle. And all I've said is that they share a common base, right? So they share this common base DE, and observe that the extent of the purple triangle and the extent of the orange triangle lives within two parallel lines. We have DE is parallel to BC. So based on the result that I had shown you on this page, what can we conclude? What we can conclude is that the area of the two triangles that we are considering must be equal because they have the same base and they both live between parallel lines. So that means that by the previous result, triangle BDE and triangle DEC have equal areas. Does everybody agree with that statement? Someone says, I'm moving too fast. Okay, so let's go back. So in particular, which part do you think would need the gap to be filled? Maybe I could quickly zoom in on that spot and help you understand it clearly. Right, so while I await that response, I will just repeat that we were considering triangle BDE, which is this triangle here, and we were which is the purple triangle, and then we were considering triangle DEC, which is the orange triangle. They share a common base. That base is the highlighted segment DE. And secondly, both those triangles lie between two parallel lines, which by the previous result infers that the areas of the two triangles must be equal. So that's what we have. So because the areas of that two triangles are equal, it means that the area of triangle BDE equals to the area of triangle DEC. So what does that then mean? Because observe that I have that the numerators of both these fractions are equal because they are the area of the same thing. And then I have that the areas in the denominators are equal because we had just seen that by the result I had stated and by comparing the areas of these two triangles, we had seen that they were equal. So I've got equal statements at the top and equal statements at the bottom. I see in the chat box that the person who initially said it was a bit too fast understands clearly now. I'm glad I was able to clear that up. So clearly, this first fraction is equal to the second fraction based on the explanation we had just gone through. And so what does that then mean? It means that AD over DB is equal to AE over EC, right? So let's write that down. And of course, in your explanation, when you are writing out your proof in your exam to get marks, please ensure that you clearly state why both the denominators had coincided, why they were equal, and how would you explain that? You would explain it using the above fact. So be very clear and concise when you are writing out your proof. Be logical. Ensure that one statement leads to the other. So if you were able to follow this, then you will not have any problem in understanding how to apply the result. So please ensure that you internalize the statement. And if you are given a situation where you have a triangle and you have a line segment that is drawn parallel to one of the sides, that you can easily see how the other two sides end up being in proportion to one another, right? So that's that main result. And now I'd like to move on to some of the other theorem statements that you are required to know when it comes to Euclidean geometry. Right, so these results, I believe, were taught to you since grade 10 and 11. So I, of course, do not have time to prove these results, but we're going to go through the statements and we're going to answer a question together. So the first result, or in particular, the first two statements tell you the following. It tells you that whenever you're given a circle with center labeled 0, and whenever you're given a chord AB, so AB is a chord. So let me just write down the statement properly. Right, so we have a circle C with center denoted by 0. We are going to let AB be a chord. What is a chord? A chord is a line segment whose endpoints lie on the circumference of a circle, as you can see here. And in particular, the endpoint is A and the other endpoint is B. So AB denotes the chord, and OP denotes okay, so we'll let AB be a chord and OP be a line drawn from the center to P on chord AB. So that's the first bit that we have to now internalize. So these are the things that are given, okay, information that's known to you. So you start off with a circle, center 0. You're given the chord AB, and you're given the line OP, where OP is drawn from the center to a point P on the chord AB. That is what you start off with. And you are then told that if whenever AP equals PB, then it implies in the first instance that the line OP is perpendicular to the line AB, right? But in the second instance, it tells you that if you start off by knowing that OP is perpendicular to AB, then you can conclude that AP is equal to PB. So we have an if and only if statement. When you start off with a circle, center, and a chord, and a line drawn from the center to a point on the chord, if you know that that line bisects the chord, meaning AP equals to PB, then you conclude that that line is perpendicular to the chord. And if you know that the line is perpendicular to the chord, then you can conclude that the line bisects the chord. And so that is the first result that you needed to remember. All right. So in the Q&A, we have two questions, and that's about recordings. Yes, recordings will be available, so there's no need to stress. Okay, so that was the first result that we needed to take note of. And the second deals with angles, but in particular at the center of the circle versus angles subtended at the circumference of a circle. So let's suppose that we start off with a particular arc, right? And so we have arc AC. So from this arc, we can then subtend an angle at the center of the circle, and we can subtend an angle somewhere, anywhere on the circumference. So that's what happens. So that angle, that point there when it touched the circumference is called B. So in this instance, the result then tells you that the angle at the center is double the size of the angle at the circumference. So that's an important result to remember. This is another diagram depicting the same thing. And then likewise, if you start off with a common arc AC, then regardless of where the angle gets subtended on the circumference of the circle, as long as it's in the opposite segment, those angles would be equal. So in particular here, B would be equal to D. And another variant of this result is that if you start off with different segments, but these segments are equal. So if you have equal segments, they will subtend the same angle, well, equal angles. That's what it says. And so as you can see, arc AC subtends B and arc FD subtends E. And B, the conclusion is that B would equal to E. So ABC equals to FED, right? And more importantly, we have another result regarding the angles in a semicircle. So whenever you have the diameter BD and we have an angle being subtended, on the circumference in this way in one part of the arc, then that angle, it turns out, has to be 90 degrees. So of course, all of these statements can be proven, it can be verified, but we are just going to be utilizing these results and we are going to apply them in specific situations. So I want us to now consider these particular results, and we are now going to answer a question together from the exam. Okay, so remember all of these things about subtending angles and angles about chords and bisection of chords and perpendicular lines. So those are important. Right, so let's go on to our question. So here is the question. Let's begin dissecting exactly what we have been given. So we're told that in this diagram, we have MP is the diameter of the circle. Right, so here is M and here is P. So clearly MP passes through the center, and here we have our center O. Okay, so we're also told that MP cuts the chord NR. Where is NR? Here is NR. So NR is clearly a chord, and we see that MP clearly cuts or intersects with that chord at T. That's happened there. We're then told that NO is the radius of the circle, and that's clearly understood because it is a line from the center drawn to a point on the circumference of the circle. So NO is the radius. And we're told that we have chords PR. Where is PR? Here's PR. MN. Where is MN? That's MN. MR. Agreed. And we're told, here we go, that angle R1 is 69. So it is 69 degrees. So that's important. Let's look at the questions. The first question says, determine, giving reasons, the size of angle R2. So we need to find out what is R2. Where is R2? Here's R2. Okay, so based on the results that we have just gone through, is there any result that you could recall that we could apply here? Considering we have been given all of this information, in particular, the first statement says that MP is the diameter of the circle. So MP passes through the center. So does anybody have any clues as to how we could proceed? Use theorem 3. Okay. So I think everybody gets the idea. We're using angles in a semicircle. Well done. So that's what we required. So let's look here. We observe that MP, as we are told, is a line that passes through the center. It is the diameter. And then we observe that that line MP subtends an angle R on the circumference. So this green triangle is a triangle in the semicircle. And so what do we know about triangles in the semicircle? We know, based on this result, that that angle there, in particular A, in this case, is 90 degrees. So that means that R is 90 degrees. So let's answer the question. R equals 90 degrees. So therefore, so you'd have to provide your reason. What is your reason? Your reason is angles in a semicircle. And then we would then compute R2. So R2 equals to 90 degrees minus 69 degrees. And that simply equals to 21 degrees. I hope everybody's followed that. Okay, so that's the first bit. Let me just add a page. Right, let's answer the next question. So the next question deals with what is angle O1? So where is O1? Here it is. We now need to compute O1. Let me also fill in the information that we know that this here is 21 degrees. And in particular, we also know that this is 90 degrees, right? So that's what we've got in place. So I'll just put that there, that is 90. Okay, so awaiting some responses in the chat box. How should we go about computing O1? Again, this is relying on the previous theorems that we had seen. Is there anything? So observe, where is O1? It is an angle that is subtended at the center. What is it subtended by? It's subtended by chord MN. So that should be a hint as to what could be applied. Right, and so we have angle at the center equals twice the angle at the circumference. So thank you for that response. And that's precisely what we require. So we see that O1 is going to equal to double 69. That's what we require. So it's double 69. So let me answer that nicely on a new page. So we're looking at question 8.1.2, if I'm not mistaken. Yes, we need angle O1. And we see that angle O1 is simply twice. So it's 2 times R1, right? Because we see that R1 is also being subtended by MN. So MN generates the angle at the center, and MN also generates the angle R1. So therefore, the angle at the center will be double the angle at R1, which is 2 times R1, which was 69 degrees. Okay, and so 2 times 69 is 138. So that's what we've got. Okay, wonderful. So we now know that angle O1 is 138. Let me again check our chat box. How are we doing? Yes, wonderful. So Chelsea, that's correct. Right, exactly what you had said. Thank you for all the wonderful suggestions. Let's look at the next question. Okay, so let me remove that line. Right, so the next question is, what is M1? So let's look at our picture. Where is M1? So M1 is here. That's what we need. So how should we go about now figuring out what is M1? Okay, we've got some responses coming in fast. Angles in the same segment. So how are we getting these angles in the same segment? Which segment, which arc are we utilizing to get out this angle in the same segment? Okay, and so we've got a response that M1 equals to R2. Wonderful. We see that M1 equals to R2 because, as someone else had said earlier, angles in the same segment, and you can see that we have NRP, and we have NMP. So from NP, we get out angle M1, and from NP, we get out angle R2. So those two angles must be equal, right? So once again, angles in the same segment. So R2 equals M1. Let's write that down. So thank you for spotting that quite quickly. So we see that M1 equals to R2, which equals to, what was R2? It was nothing but 21 degrees. And we would like to specify angles in the same segment. Great. And now we have our final question. Calculate M2 if it is given that NO is parallel to PR. So we're told that NO is parallel to PR. And we need to calculate M2. Where is M2? This is M2. So that's what we want. All right, suggestions once again. We need to calculate M2. We've got some responses. Okay, so we've got angles opposite equal sides. So that's one of the suggestions that we've gotten. We're given parallel lines. So let me point out the following. Observe that M2 lies in the following triangle. So this is to help you see how we're going to get this out. So look at my blue triangle that I'm drawing. So this blue triangle, if we had to draw it again, so that's M, that's R, and that's P. We already know that R is 90 degrees, right? That angle is 90 degrees. And this is what we want to find. So wouldn't you agree that if I find angle P, I would be able to determine what M2 is? So that is the approach that we take here. So we try to find P utilizing the fact that NO is parallel to PR. Is there a way to determine P using the fact that NO is parallel to PR? Let me check the chat box. Alternate angles somehow? Yes. So yes, we are going to be using alternate angles. So thanks for that response. So what we need to observe here again, utilizing a trick from earlier, is observe that M1, which we had just determined, is related to O2. Do you see that? Do you see that M1 is related somehow to O2, angle O2? Because observe that O2 is an angle at the center, right? Subtended by MP. And what do we know about angles at the center? It is twice the angle at the circumference, isn't that so? So it turns out that O2 is equal to twice M1. Do we all see that? Wonderful. And I see the responses that O2 is 42 degrees. Perfect. So that's what we utilize. So for this bit, we've got 8.1.4. We first observe that O2 is equal, not O squared, angle O2 is equal to angle, okay, equal to twice M1, which is 2 times 21 degrees, which is 41 degrees. And how did we see this? Because of angles at the center, right? So angle at the center. So I hope everybody followed that. So I now know that O2 is 42 degrees. And then, as someone had mentioned earlier, alternate angles, right? So we then see, because we've got parallel things in here, that this 42 degrees is precisely angle P. Do we all agree with that? Using alternate angles. So let me refresh your memory in here. When you have parallel lines, right? So we have that the following is true, that alternate angles are equal. So that is also true. And so that's precisely what we're utilizing. So therefore, I can then say that P equals to O2, which means P equals to 41 degrees. And so because I know that P is, sorry, it's 42 degrees, why did I write down 41? When I put 42 in the diagram. So that is 42. So it's 42 degrees. And then let's go back to the diagram. We're now sitting in this triangle. So there's the 42 degrees. We've got 42 degrees, we've got 90 degrees and M2. Can't we solve for M2? How do we do that? Angles of a triangle sum to 180 degrees. And so we see that M2 equals to 180 degrees minus 90 minus 42. Isn't that so? And what answer do you get in here? You get an answer of 48. And so this is the final answer in this. That is M2. Let's put that in, 48 degrees. And so the sum, 48, 42, and 90 sums to 180, ensuring that the sum of the angles in a triangle is 180 degrees. So did everybody follow that? Okay, so yes, we've got a few responses. So I'm glad that you all did. We have now come to the end of this session. We will make this PDF available to you via the NITheCS website as well as the recording. So please look out in your emails for all further details and communications. We will be continuing with these lessons on a monthly basis. So look out for upcoming communication. It will be sent out to you. Thank you for joining us today. I hope you all stay safe and have a wonderful weekend.
Thank you very much, Serena, from all of us, yeah, for another very nice and useful lecture. I'm pretty sure that everybody profited from your lecture. Thank you very much. Yeah.
Thank you.
Have a good evening, and good evening to everyone. Yeah.